Yes.
Okay, first of all, before we get started here, I want to say that I'll forgive all of you after last night if you don't vote me to be the best speaker.
Guilt, using guilt, that works sometimes.
So anyway, I was interested in what we could do to test some random number generators, and I was looking at some that are notorious failures, and specifically I was focusing on our old standard 999X. So I did all of my tests on my computer. I'd sure like to get some new overlays for this thing. It's right here.
Eric,
Can you do it?
I can.
Yes.
Eric tells me.
So what kind of tests can we do on random number generators? Well, the things about 997X that you have to know is basically it follows two main guidelines. The first guideline is in the Bureau of Standards, the Handbook of Mathematical Functions. They tell you to use a multiplier that's very close to the square root of the modulus. Well, you can't get much closer than that if the modulus is 1,000,000. And if you go in Knuth, in which he regurgitates an earlier theorem, but Knuth has a theorem that says that a good multiplier that gives you maximum period, it would be 197 modulo, let's see, it's 197 plus some multiple of 200. So it's 197 mod 200. And once again, that's what we have here. So the origins of this are way back in the HP 97 days. So I guess that's why they liked it 997 as a multiplier.
No, I don't think that.
The old stat packs, maybe 65, had 997 times a random number, take the fraction, get the new random number.
Yeah,
And it's a good one.
yeah. So 997 fills all of the guidelines for what's a good multiplier. Now, if you're working on those older calculators that didn't have quite as many digits as we have now, this was probably as good as you could get. And it's fast, of course. It's a single. If you have recall arithmetic, it's only a single multiply followed by the fractional part followed by a store. It's very quick. So the question is, how many random numbers can you generate with this thing? Well, if you look, you're multiplying by 997. So if you have a starting seed that is a multiple of 5, the last digit is always going to be 5. If you have a starting seed that's an even number, all the remaining random numbers will be even numbers. So you don't want any multiples of 2 or 5. So that knocks you down to what, 40,000, 400,000 out of the million possibles. And so you get terrible results with a starting seed of 0.2, because you can figure it out. It'll go 0.2, 0.4, etc. And you'll go into a cycle of 4. But if you start with 2.0001, you can get good results. And it turns out there's 8 good starting seeds. Now I multiplied these by 1,000,000 just so we can work this out. What did I do?
Don't touch the screen.
So I found that, anyway, I found these are the good starting seeds. Now, this shows how the initial seed affects the period. And one of the things you like in random number generator is to get as many as possible. And as you can see, if you want to increase the number of random numbers beyond 50,000, you can use a starting seed that uses a couple extra digits. It turns out a couple extra digits really goes a long way towards improving this thing. So what can go wrong? So I wanted to do a simple Monte Carlo integration. And here it just matters only what numbers you get. It doesn't matter the order, because you're just averaging this function over the interval from 0 to 1. And in a calculator you can do that very easily with the sigma plus function. And what happens? Well, I tried several random number generators here. 997X, it worked pretty good until you got to 12,500 for n. See, n is here. 12,500. It was okay at 499. At 500, you had a kind of an aliasing with the lesser significant digits of the random numbers. And there's algorithm F. You can guess what that must be. That seemed to do okay. Algorithm P, which only one other person in this audience probably knows what it is. That would be Joe. And then this is a built-in random number generator. So they all work pretty well, except when they get these resonances. And we'll see a little more about that later. So that's an integration gone bad. So what's the thing the main thing we want? We want uniform distribution. And there's different ways we can quantify that. Power spectrum, moments, equal numbers in bins. And then there's something I call a comb test. And basically in a comb test, you multiply the random, your generated random number by some large integer, say 1,000. And then you take the fractional part of what's left. So you're only looking at the least significant digits. So here's what the power spectrum looked like, at least for the first 52 harmonics. And I took the tall blades of grass after I did this, and I re-examined them. I ran the tests again, and they weren't as high. So all of these should actually be close to 0. And they generally are. Now if I took this and extended this up to 12,500, you would see a big spike there. So here's what the moments look like. The moments are pretty much what you'd expect. Here I worked out the exact moment with calculus. And instead of analyzing the random number x, I use the y sub I. So it would be symmetric around 0, and I wouldn't have to worry about subtracting the mean. And here's the discrepancies in the moments. Oh, excuse me. I mistakenly called algorithm P JH here. I didn't catch that J. I don't know why. If you look for example at algorithm P, you see that the moments, the even moments tend to be on the high side, which means that the random numbers are a little bit congregate a little bit out more towards the edges of the interval. And if you look at the 997X, it's the opposite. They tend to be in a little bit, but not significantly. So now, the chi-square test, okay, what's the, yes?
This idea of significance, I
Of
think
what?
all of us have seen movies where they go to Vegas and they see a little bias in the wheel. You know, they're looking for,
Okay, okay, there's in information theory, there's an epic legend about Claude Shannon. He's the founder of information theory. And back in the 1960s, I don't know what he was doing back then, but he went to he went to a casino in Reno, and he found that if a roulette wheel hit one number 6% more than it should, if the probability was 1.06 times 1 over 37 or whatever it is, he could just bet on that number consistently, and in the long run, on the average, he would win. But in order to determine the probability that probability existed, he had to observe the wheel for 3 days. So he put together a team, and they went there and they observed a bunch of wheels, and after observing a number of wheels, they finally found one that was sufficiently out of balance, and they started betting on it. And the legend says that he ended up with a net profit of $3,000, at which point the casino management asked him to leave. I'm so proud to be a citizen of Nevada. So anyway, what we do here is you have this definition of the chi-square statistic, and so you're taking your random numbers or groups of random numbers and putting them into bins. And if you notice, if you notice this thing, this expression, it looks a little bit like standard deviation, doesn't it?
Yeah.
And in general, when you have a large collection of numbers and you want to find out how spread out they are, how different they are from being all the same, standard deviation is the thing you use. Well, it turns out that to compute this chi-square distribution, all you do is use a sigma plus function in the calculator, and when you're done, you get your S from the statistic function, and you square that gives you the variance, and then you multiply by n minus 1 and divide by the mean, and then you've got, see, here's the mean here, and I just went to the next one. Okay, so it's easy to calculate the chi-square statistic just using the statistical functions that are in the calculator. So now the next question is how to define the bins, right? Well, Namir has already done that. He just sliced it into 10 chunks and 10 bins, and I wanted to get more bins than that. So, whoops, there. Okay, now, another comb testing. Okay, as I mentioned earlier, what you do in comb testing is examine the less significant digits. And so if you wanted to do a test, say, of the second digit, you take your random number, multiply it by 10, and take the fractional part. And then multiply that by 10, and that defines the bin, if you were going with 10 bins. So let's look at what we have here. At the time I did this, I only could have 80 bins, and so if a bin that I calculated went beyond 80, I ignored it, because if the first 80 of the bins are non-uniform, then the thing's going to fail anyway. And if they are all uniform and have a very low chi-square score, then the remainder are probably okay. If you wanted to be completely thorough, what you could do is, instead of chopping off the last 10 of the one, or the last 20 of the 100 bins, you could chop off the first 20, and then you have two things overlaid. So here's what we found. If you divide the random numbers into 80 bins, you get a chi-square score of 0.017. And that's very good. That's very close to a uniform distribution. That's the chi-square probability. That means that if the thing is totally random, there's only a 0.017 chance of getting closer to uniform than what 997X gave you. That's very uniform. Now, uniformity in a random number generator isn't all that matters, of course. The most uniform generator imaginable is what I call, it's not 997X, it's 1 plus. If you take 0.000001 and just add that to the previous random number, you'll get something that's absolutely uniform in the long run. But this shows you where things start to go bad. So here I multiplied by 10, and as you can see, the second digit is also pretty good for 997X. The Pell series broke down on the second digit. And going on, now you get to the third digit and on down. They're all of these are total failures, except for the one that's built into the calculator. So that's pretty much the result. If you use 997X, you know you've got two good random numbers, two good random digits. Whoops. So you can do something like this to combine two random numbers and get them two digits at a time. Of course, there's a sacrifice in speed. Yes?
When you say combine, you add them or multiply them?
Huh? You take the first random number, and multiply it by 100, take the floor. That gives you the first two digits. Take the second random number, add it in, and then divide the sum by 100, and that gives you, now you should have 4 good random digits. So, okay, now, so far we've only talked about a single random number. We're interested in the serial correlation. We want our random number to be independent of all the previous random numbers. So what you do is you test in hyperspace. You can test in the cross product of two random numbers, and they can have different gaps. So that leads you into something called the autocorrelation function. And you can do bin testing in the chi-squared, and and permutation testing. That's an interesting one. Okay, so this is just how you organize them. You see, for a correlation of two random numbers, you can have a power of a random number. You can have a lag. How many random numbers till you get to the second one, and then the power of the second one. So there's really a lot of variables to test for, and there's a thing in mathematics. A guy named Cantor back in the 19th century proved that the number of fractions is no greater than the number of whole numbers. So there's a lot of tests here, and Knuth has written in his book that the number of tests you can do is endless, and he wasn't kidding. But it's countably endless. Okay. So that shows you about how many different tests you could do. Okay, now I tried to get this chart from Excel into PowerPoint.
It's called screen
And
capture.
this is the autocovariances. And once again, the tall blade of grass there, and the legend, they knocked out the legend, so I don't know which one is which. But I did rerun the tall blade of grass a second time, and it wasn't as high. So at least up to the 41st harmonic, up to delays of 41, there aren't any strong correlations. Now, if you want to test triples, there's so many tests you can do with this kind of testing that it's just, I wouldn't even attempt it. Okay, so here's some implementation considerations on it, because this is my computer. 100 registers, and you need some of those to do the random numbers. So you can reject bins that are too high, and you can combine bins, and you can do digit packing to increase the storage, that's what I actually have. Since I did this report, I implemented. I now have 4 bins in each real number in each register, so I can go up to 360. So if you want to do permutation testing, you have to use a factorial numbering system. And this goes back to a guy named Lamer back in the 1950s, I think. And you want to have these random number generator. You want to have these things generated with all permutations equally likely. So you have to identify the permutation and then increment the appropriate bin according to what permutation you have. And this is how you do it. You encode them with a factorial numbering system. So here's some tests that we did. Okay, 997X did fine until you try to consider permutations of 5 of them. If you have a group of 5, the permutations are not as random as you like. Everything else is okay. Now, for many problems, that might not matter at all. 997XS, okay, that's 997X with steroids. When 997X failed, I added 2 digits, so I used a starting seed of 10 to the minus 8th. And I increased the multiplier to 997, which once again is consistent with the recommendations of the Handbook of Mathematical Functions and with Knuth. And it passed fine. F and P failed, and the built-in random number generator passed everything. So this just shows you the amount of work. Now, the other thing we sometimes like to have is points that are uniformly distributed on a disk. And so how do you divide the disk into areas of equal probability, equal area, to calculate the bins? And if you notice here, you have 1, 3, 5, 7. The next zone out would have 9. It's a sum of the odd numbers. The sum of the odd numbers, of course, is a perfect square. So it turns out it's easy to calculate the bin number from the two random numbers. And let's see, I got up to 9 zones. Okay, now the other thing is, if you want to study this at the mathematical level, you can go into Knuth and do the random number. You can study how the random number works and do a lot of number theory. And the problem is that in many cases you don't have access to that. You don't know what it's actually doing. All you have is the numbers that it spits out. But with 997, you know what it is. So anyway, that's about it. I'm going to look into this a little further. I want to use the KS statistics. I want to look at the Walsh and the Hadamard transforms, and I don't know about secret hidden messages. If you look at the Hebrew text of the Old Testament, maybe you'll find some. They call that gematria. And there's still lots to do on this. Maybe next year I'll have more. So that's about it.